In the previous video, you learned how to derive the lens maker equation by combining two equations for spherical surface for each of the surface that you have for the lens. Okay, and we mentioned that this equation here can be it's general for any kind of lenses that we will encounter. So now we'll double check whether it's true or not. Okay, so let's see today our lens here will be a concave lens instead of a convex, a biconvex, or a meniscus lens. So if you have a concave lens, let's try to think. Concave lens also have two surfaces, one this side, one the other side. And if you try to create the equation for each of the spherical surface, you notice that the equation will look exactly the same. Means by NA will still be NA, NB will still be NB, NB minus NA will still be NB minus NA. U1, V1 is general term, we will still use U1 and V1, and we will still use R1. The only difference that we might encounter is that U1 might be a positive or negative value, V1 might be a positive or negative value, R1 might be a positive or negative value. The value that is carried by U, V, and R might change from positive to negative according to what kind of lens that we use. Okay, NA and B, it still depends on the surrounding medium's refracting index and the lens material's refracting index. So if you don't change those things will still remain the same. Or even if you change, the symbol will still be NA and B, just to change the value carried by it. So I'm trying to say here is the equation will look exactly the same, except that the number might change, or the sign of the value that it carries might change. So in that case, this will still be the same equation, this will still be the same equation for any kind of lens. So this equation, we can say that it's general for any kind of lenses. We know that this R1 and R2 is the tricky part that we're going to study. Okay, because R1 and R2 is the thing that change based on different kind of lenses that we have. NB and NA is usually just a refracting index. There's nothing much tricky about it. So we'll try to look at different kind of lenses and try to see whether the R1 and R2, what kind of sign should we assign for those for their radii of curvature. Okay, so we are going to study for converging lens. So we learned from the 2 videos ago that focal length must be positive for converging lens. So we'll try to determine the sign of the focal length, and we predict that it should be positive for every kind of converging lens. So let's start with the first one. We have the double convex lens. Double convex lens is a lens where you have convex spherical surface on both sides of the lens. So you can see that it consists of two surfaces, both surface bulging outwards. It is curving outwards. That's why I call it biconvex. The bi, you can think of it as bicycle. Bicycle have two wheels. Bi, okay, this biconvex means two. Okay, so two convex surface. Okay, so light will travel incident on the first spherical surface and bend in towards the lens material. Then will travel in the lens material until it strikes on the second spherical surface. Then you exit the lens material back to the surrounding medium. Okay, so you try to determine whether this R1 here should be positive or negative. This R2 here should be positive or negative. For R1, first surface over here, the center of curvature should be on the right of this first spherical surface. Okay, it should be on the right because if you trace out the circle based on this curve over here, you know that the circle looks somewhere around here. So your center of curvature will be somewhere here. Okay, your refracting ray will also incident over here, then get refracted over here. So the refracted ray is also on the right hand side of the first spherical surface. The radius, the center of curvature is also on the right of the first surface. So they are on the same side of the spherical surface. Therefore, we know that this R1 here should be positive. Same side, positive. Okay, for R2, we know that if we extend this curve here, we see that the circle will be on this side. Therefore, the center of curvature should be on the left-hand side of the second spherical surface. But the ray will be incidenting on the left-hand side, then it will get refracted and go out to the surrounding medium, therefore on the right-hand side of the second spherical surface. So the refracted ray is on the right-hand side of the spherical surface, whereas the center of curvature is on the left-hand side of the spherical surface. So these two are on opposite side of the spherical surface, therefore R2 should be negative. Okay, so what will happen if we sub in positive R1 and negative R2? We will see that if we sub in positive for R1 and negative for R2, we will see that the negative and the negative over here will interact with each other, so it will be a positive second term. So one term which is positive plus another term which is also positive, you'll get an answer which is positive. And for the first bracket over here, the term n material divided by n medium should be usually greater than 1. Why is it usually greater than 1? Because we usually have our lens built in a way that it is denser than the surrounding medium. Let's say if our surrounding medium is air, then usually the lens is made of glass. Therefore, glass is much denser than the surrounding air. So the glass should have a higher refractive index compared to the surrounding air. So if you have something large for numerator, something smaller for its denominator, you'll find that this fraction here will be larger than 1. And if we have something larger than 1 minus 1, then we will have something larger minus something smaller. So larger minus smaller stuff, you get a positive answer for this bracket over here. So if something positive multiplied by something positive, you also get a positive answer. So you know 1 over f will be positive, and therefore f should also be positive, just like what we predict out here. It should be a positive focal length. Okay, let's try for another lens. Let's say you have a planar-convex lens. So planar-convex lens is made up of one plane surface, a 2D plane surface, and a convex surface. Okay, so if you decompose it, you have a flat surface and the surface curving outwards. So now light will be incident on this first refracting surface, enter the lens material, then strikes on the second refracting surface, then exit the lens material into the surrounding medium. So for the first surface over here, since it's flat, you can think of it as like the radius of curvature, it's infinite. Okay, if you have an extremely large circle, then cutting a small portion of it, you might see that the portion looks like a straight line. Just like you can see your ground is flat when the earth is extremely huge. So you can't see the curve. You can't see the curve caused by the extremely large circle. Because what you can see is only a small portion, and what you can see is only the flat portion. So in that case, you can think of the radius of curvature, it's infinite for this case. And if the radius of curvature is infinite, you didn't need to care whether it's on the left hand side or the right hand side, whether it should be positive or negative. Because when you sub it inside the infinite value, no matter it's positive or negative, you get the answer as 0 for this case. So you just need to know R1 is equals to infinite. For the second refracting surface, the center of curvature will be on this side, because if you extend the circle, it should be something like this. So the center of curvature is on the left hand side, whereas the refracted ray will be on the right hand side, coming out from the lens material into the surrounding medium. So in that case, they are on opposite side, refracted ray on right hand side, center of curvature on left hand side. Therefore, opposite side, we should get negative R2. Okay, so what does that imply over here? If we sub in infinite for R1 and sub in a negative value for R2, the negative and the negative here will interact to give you a positive value. Then you will have 1 over infinite, which is 0. So a 0 value plus a positive value, you get something positive here. Okay, similar to the first lens, here should also be positive. So positive multiplied by positive, you will still get a positive value for your 1 over f. Therefore, f should be positive as well. Okay, everything still follows according to our prediction here. So let's look at another converging lens, which is a convex meniscus. Okay, convex meniscus is quite an interesting lens because it's made of two surfaces. One is convex, another one is concave. Okay, but why do we call it convex meniscus instead of calling it convex concave? Okay, it's just that the convex refracting surface over here, it's much curvier compared to the concave refracting surface. The convex surface is the one that is curving outwards, whereas the concave surface is the one that is curving inwards. Okay, curving inwards towards the lens. So it's curving out of the lens. Okay, so why do you call it convex? Is because the convex surface is much curvier compared to the concave surface. And what does that mean? The convex surface here is dominating the refraction of light that happens. So it means that this convex surface here will bend the light stronger compared to the bend that is caused by the concave surface. And because of that, the convex surface is dominating the refraction that occurs. It's just a mild refraction caused by the concave surface. Therefore, since the convex surface is dominating, we call it the convex meniscus. Okay, so for the first surface, our center of curvature will be on the right. Okay, whereas our refracted ray will be also on the right hand side because it's entering the lens material. So the refracted ray and the center of curvature are on the same side. Therefore, our R1 should be positive. Okay, how about R2? For R2, our radius of curvature will also be on the right. Okay, our radius of curvature will be on the right, and our refracted ray will also be on the right. So they are on the same side of the refracting surfaces. Therefore, R2 should also be positive. Okay, so what does that imply? If you sub in a positive value and a positive value, now you might have problem with determining whether the second bracket here should be positive or negative. But if you look at these two diagrams here, you see that R1, this first refracting surface here is much curvier compared to the second refracting surface. A much curvier refracting surface, you can think of it as made of a sphere that is much smaller in size. Okay, compared to a less curvy surface, is made out of a sphere that is much larger in size. Okay, if you want to think why is it so, you can think of the extreme. For a straight line, it's very not curvy, right? It's very not curvy because the radius of curvature is extremely large, the circle is extremely big. Therefore, you see a flat surface. So if you see a less curvy surface, it will be made out of a circle that is very huge compared to a surface that is curvier. So what I'm trying to say here is R1 should be a smaller value because it's made out of a smaller sphere. R2 should be a larger value because it's made out of a larger sphere. So I should write it down. R1 will be smaller compared to R2. Okay, and if we know that, then this one will be a positive small value for R1. Then you have a positive big value for R2. Then what does that mean is 1 over R1 here will be a positive big value. Okay, whereas for 1 over R2, it should be a positive small value. Okay, I'm just writing this is for R, this is for 1 over R. So in that case, positive big minus positive small, big minus small is just a positive value. Okay, then we also know that this part is also positive. And 1 over f here should also be positive. So we know that the focal length will be positive as well, just as what we predict. Okay, so everything seems fine here. So we see that for all three kind of lenses here, you get positive focal length. Why is it so? Because all three lenses here are converging lenses. Why do we say so? We see that the center portion of the lens, the center portion, it's thicker compared to the edge of the lens, which is the top and bottom portion of the lens. The top and bottom are usually thinner compared to the center portion of the lens. And we call all these lens converging lens or positive lens. Okay. I have also prepared another 3 kind of lenses which are for diverging lenses. So for diverging lenses, they should have negative focal length, and I will list out everything because I think you should be able to determine it for yourself. I'll just try to elaborate on the third lens over here, which is a concave meniscus. For concave meniscus, it's made of a convex and a concave surface as usual, just that the convex surface here will be less curvy compared to the concave surface. It means by the concave surface here will be dominating the refraction that happens when light passes through the lens. It will be a mild refraction at R1, at surface 1, and it will be a stronger refraction at surface 2. Therefore, we say this concave surface here is dominating the refraction. Therefore, we call it a concave meniscus. So for the first refracting surface, the center of curvature is on the right, and the refracted ray is also on the right. So they are on the same side. Therefore, we know that R1 will be positive. For the second surface over here, you see that the radius, the center of curvature will be on the right as well, and the refracted ray will also be on the right. So the center of curvature and the refracted ray are both on the right hand side. So what does that mean? It tells you that R2 should also be positive because they are on the same side. So if we sub that in, we encounter a situation similar to the convex meniscus just now. You will get a positive value for R1 and a positive value for R2 as well. But you can see here that R1 here is larger compared to R2 because R1 here is nearly flat already. So nearly flat means by the center must be very, very far away. So you have a large radius of curvature. So if our R is like this, then we know that R1 here is positive big, R2 here is positive small. And then if you put it into the 1 over, you reciprocate it, then what you get is, you get a positive small for the first term, 1 over R1. Then you get a positive big for the second term, which is 1 over R2. And if you take something small minus something big, what do you get? You get a negative value. So if you get negative value multiplied by a positive value, what you will get will be a negative value. So negative value tells you here that the focal length should be negative, just like what we predict for diverging lens. Okay, all of this diverging lens here has a center portion which is much thinner than the edge of the lens itself. Okay, so you can determine whether it's diverging or converging just by comparing the center and the edge. Okay, another way of determining whether it's diverging or converging, look at the focal length, whether it's positive or negative or not. Okay, I just want to mention one last thing before I move on to a question. For a concave meniscus over here, even you do a horizontal flip, means by you flip so that you will encounter a concave surface followed by a convex surface, would it change it from a concave meniscus to a convex meniscus? The answer is no. No matter which side you orient your meniscus lens, it will still be a concave meniscus for this case. Okay, because the focal length is equal on both sides of the lens. So it doesn't matter whether you flip it this way, you keep it this way, or you flip it so that the convex face the another side. Okay, it will still be a concave meniscus. The way you determine whether it's concave meniscus or convex meniscus only depends on if it's convex meniscus, the center should be thicker than the edge, then it's convex meniscus. If the center is thinner than the edge, then you get a concave meniscus. Okay, so that's all the things I want to talk about for lens maker equation. So let's try and apply what we learned in the question.